Let's see if we can get this. There we go. So, Unit 8, Sound and Waves. I love this unit. I think it's very interesting. It has a lot of hands-on application that we'll use, and so it's important that you're going through the notes beforehand, before the videos, because there's a lot of like visual aspects to this and animations that are done, so you can see the vibrations and the oscillations and those kinds of things. Okay, so we have 5 learning targets that we're going to cover, and today we're going to go over learning target number 1. And so this talks about period, frequency, and wavelength, and we'll identify those components of a wave, and amplitude. And then we're going to be using a couple different equations for frequency, and then a wave speed equation. Okay, so you've gone through and you've talked about how like a vibration is a back and forth motion, about an equilibrium position. Okay, and so we see this a lot. There's so many different examples of things that vibrate. Maybe like a guitar string, right? And it goes back and forth along an equilibrium that eventually it'll return to, right? Or a bowstring. What else? Think of some examples and let's get those written down for vibrations. One that you may not have thought about is bridges actually do vibrate, and there's some really interesting and amazing videos of finding bridges that will continue to vibrate when they find that, frequency, and it can cause some major havoc. So lots of different things that vibrate. Oh, and then we defined in our notes what a wave is, and we can kind of draw that conclusion and comparison of a wave to a vibration. And one important item with waves, let's see, where do I have this? One important item to realize with a wave is that the mass or the medium in which the wave is propagating through, that we don't have any displacement through that medium. Like, think of water in an ocean wave. Like, yes, it goes back and forth and we see displacement, but overall it'll settle back into the original position. Okay. All right, pendulums. We have some great animations in the notes of our pendulums. And what I want to talk about right now is the period of a pendulum is dependent on the length of the pendulum. Okay? So let's talk about this. First, period. What is the period of a wave? Period is the time it takes for a complete wave to occur. Okay? Or vibration to occur. So if we have a pendulum and we drop that pendulum and it swings back to the original position, it's the time it takes for that oscillation to occur. Okay, from starting at one point and ending at the same point, an entire wave. And so the period does depend on the length of the pendulum. And what I want you to think about for a moment is, what is that relationship between period and length of the pendulum? Do you think it's proportional? So reminder, proportional means that when one gets bigger, the other one gets bigger. If one gets smaller, the other one gets smaller. So a good example of proportional would be if the length of the pendulum increases, the period of time it takes to go from here back to where it was will also increase. And we have inversely proportional, which it means when one gets big, the other one gets small. So example of that would be if we increase the length of the pendulum, then we decrease the amount of time it takes for the pendulum to start at one point and then return to the same point. And then we've also seen inverse squared. And so you saw that with gravity and with our electronics, like electromagnetic forces, we saw that. So what do you think? I want you to make a prediction about that and get that recorded below. Okay? And so what happens is as we increase the length of the pendulum, the longer it takes for it to return back to that position. And so they are proportional. When one gets big, the other one gets big. When one is small, the other one gets small. So if we increase the length, we increase the period. Okay, so harmonic motion, man, we have so many names for kind of the same thing. Like we have wave, vibration, harmonic motion, oscillatory motion, and we're talking about this, progression where we're starting somewhere as a wave moves through a medium, right? And so we get this kind of like back and forth vibration of water or of air. And so we see that for vibrations, waves, harmonics, etc. Okay. Okay. Now, for this part here, absolutely, there's a great animation of this that I want you to go through in your notes, and then I want you to take some time to draw a picture of what's happening there. Is essentially what we see is a pendulum is swinging back and forth, and it's like a paper was like drug underneath it, so we can kind of see that motion of the pendulum as time is passing. And so maybe I can see. Okay, so if time's passing and the pendulum's kind of going back and forth like this, and if we drag the paper across, we get a sine wave because it'll go back and forth and back and forth, and so then we end up with something like this. Okay? Here's what you're going to need to know. You're going to need to know, so add this to your notes here, that wavelength is the distance between two equivalent points on a wave. Okay, so one more time. Wavelength, make sure you get this written down up here, over there. The distance between two equivalent points on a wave. Usually we like to identify peaks or troughs because those are easy to see. And so we can go from like peak to peak or trough to trough, and that would be an entire wavelength. We've seen what, the distance it takes to complete that entire motion. And so that's why from like node to node there, that is not a complete wavelength. Okay, so peak to peak, trough to trough. So that's wavelength. And then we have amplitude, which is from the origin. Okay, so that's another common mistake there. A lot of students will tell me amplitude is like from the crest all the way down to the trough, and that's not the case. That would be twice the amplitude. So it's either from the origin to the crest or the origin to the trough. And wavelength and amplitude are both measured in meters, or like a distance measurement. Centimeters, millimeters, or smaller, bigger as well. Okay. So we've talked about wavelength and amplitude. Reminder about period, the time it takes for a complete wave or vibration to occur. And so if this wave was moving, okay, if it was, right, with our pendulum and it was going across there, it would be the time that it took for that pendulum to go from one place and then go back to where it ended, right? And so one way of looking at this wave here, a period is the time it takes for a complete wavelength to occur or to pass a certain point. You could think about standing on the end of the pier, okay? We're watching the ocean waves come in, and the time it takes for a new crest of an ocean wave to hit the dock, that time in between crests, that would be a frequency. Or sorry, then there's period waves per second. That's frequency. Okay, so that example of the time that it takes for like how many waves occur per second. Okay, so back to our example here because I want to be really clear about this. So the time in between those waves, the crests of the waves when they hit the dock, that would be a period. The amount of waves per given time frame, usually 1 second, that's a frequency. Waves per time period. Okay, so let's just say that it's a really windy, blustery day and a lot of waves are hitting the dock, and let's say within 2 seconds, or no, sorry, within 1 second 2 waves hit the dock, then the frequency would be 2 waves per second. Okay, so frequency, the number of oscillations, waves, etc. an object makes in a unit of time. Okay, now we're going to represent frequency with the units of hertz. And so a frequency of 1 cycle, or from like crest to crest, per second, that's hertz. Okay, the symbol hertz, right? And that's the same as per second, or seconds to the -1. Okay. Now I want you to take a moment, and we've talked about period and we've talked about frequency, and I want you to give this a go. What do you think the difference might be between the speed of a wave and frequency of a wave? Okay. And then when you get back, we'll talk about that, and then we'll go into radio waves for a little bit.